Pierwszą część pozwolę sobie zaprezentować w języku polskim, a kolejną część wspólnie już z kolegami z Ansysa będziemy prowadzili w języku angielskim. Także witam Państwa bardzo serdecznie na dzisiejszym webinarium, które poświęcone będzie tematom niezawodności elektroniki. Bardzo cieszymy się przede wszystkim z tego faktu, że tak licznie Państwo wzięli udział w naszym webinarium, także zaczynamy. Na początek opowiem trochę o Ansysie, opowiem trochę o nas, natomiast taka informacja, gdyby ktoś w trakcie miał jakiekolwiek pytania, to prosiłbym, żeby zadawać je albo bezpośrednio tak w tym panelu Q&A, który Państwo posiadacie, lub też można zadawać je na czacie, ale myślę, że ten panel Q&A będzie odpowiednim miejscem do tego, żeby te pytania zadawać. Także zaczynamy. Na początku chciałbym powiedzieć co nieco na temat firmy Mesko. Nasze biuro inżynierskie tak powstało w 1994 roku, no i od początku jesteśmy związani z Ansysem. Na początku wykonywaliśmy symulacje numeryczne, natomiast w trakcie staliśmy się dystrybutorem oprogramowania Ansys. No i jesteśmy dystrybutorem oprogramowania Ansys na terenie Polski i to, czym możemy się pochwalić, że jesteśmy Elite Channel Partnerem, czyli należymy do elitarnego grona przedstawicieli Ansysa na świecie, którzy mogą się tym tytułem pochwalić. No i wynika to przede wszystkim z tego faktu, że doceniona została jakość świadczonych przez nas usług, no i generalnie jesteśmy z tego faktu bardzo zadowoleni. Jeżeli chodzi o oprogramowanie Ansys, to zajmujemy się już nim i mamy doświadczenie ponad 25-letnie. Świadczymy usługi z zakresu symulacji numerycznych, tak jak wspominałem, również dystrybuujemy oprogramowanie na terenie Polski, ale również świadczymy usługi w formie kursów i szkoleń, czy to dedykowanych, czy też ogólnodostępnych dla naszych klientów, nie tylko. To, czym się możemy pochwalić, że rok do roku w naszych kursach bierze udział ponad 700 osób. Mesko to obecnie ponad 20 osób, liczni partnerzy na uczelniach, no i zajmujemy się całym portfolio ansysowym, tak? Ponieważ Ansys to nie tylko termika, to nie tylko rzeczy związane z niezawodnością elektroniki, ale także obliczenia mechaniczne, przepływowe i ogólnie elektromagnetyczne również. Pozwolę sobie przejść dalej. Tutaj chciałbym zadać pytanie, dlaczego symulacja? Myślę, że część z Państwa już wie dlaczego, albo też potrafi sobie odpowiedzieć na to pytanie. Natomiast gdyby ktoś z Was zastanawiał się, dlaczego ta symulacja jest taka ważna i staje się tutaj istotną rzeczą, tak, w samym chociażby procesie projektowania urządzenia, to myślę, że najlepiej pokazuje to pytanie, właściwie odpowiedzią najlepszą na to pytanie jest w tym przypadku ta ciężarówka, w tym konkretnym przypadku koło odleciało, no i to, co można sobie zadać pytanie, dlaczego tak się stało, tak? Czy była to jakaś wada materiałowa, czy na przykład użytkownik używał tego produktu niezgodnie z jego przeznaczeniem. No i tutaj za pomocą symulacji komputerowej możemy przede wszystkim zbadać przyczyny tego zdarzenia, możemy coś zweryfikować normowo, ale to, co dla mnie, tak, jako inżyniera jest najważniejsze, to przede wszystkim fakt poznania lepiej mojego produktu. Symulacja komputerowa pozwala nam na lepszą weryfikację naszego produktu, zanim trafi on na rynek końcowy, ale przede wszystkim to, co symulacja komputerowa mi umożliwia, to zobaczenie rzeczy, których ja nie widzę gołym okiem. Tak? No nie znam jeszcze osoby, która widziała indukcję magnetyczną B, tak? na oczy. Więc w tym przypadku te rzeczy możemy zobaczyć na ekranie komputera i możemy podjąć konkretne decyzje, czy coś uprościć, czy na przykład gdzieś nie dodać materiału, albo czy nasze urządzenie nie ma jakichś słabych stron z punktu widzenia konstrukcyjnego. Tyle się mówi o rozwoju produktu, natomiast my jako Mesko tak, popularyzujemy tak, wiedzę na temat symulacji komputerowej, więc chciałbym Państwu powiedzieć, jak ważny jest rozwój produktu w oparciu o symulację komputerową. Bardzo często, jeżeli spotykamy się z klientami, to podchodzą do procesu projektowania takiego klasycznego, tak, gdzie mamy jakiś pomysł, tworzymy geometrię w programach CAD-owskich, wykonujemy fizyczny prototyp, testujemy, robimy jakieś dodatkowe analizy i wszystko świetnie jest, kiedy udaje nam się to osiągnąć za pierwszym razem, tak? Kiedy od razu mamy gotowy produkt, który możemy zaoferować naszym klientom. Natomiast często tak się nie zdarza, no i każdy z nas chciałby, żeby udało się od pierwszego strzału uzyskać ten produkt, który możemy już zaoferować na rynku. Natomiast zdarza się tak często, że niestety musimy wprowadzać pewnego rodzaju poprawki. No i te poprawki kosztują pieniądze, a czasami nawet duże pieniądze. Najgorzej jest, kiedy trafimy w tą pętlę zwrotną i nie będziemy w stanie dostarczyć produktu. Bardzo często zdarza się też tak, że mamy bardzo krótki czas, w którym musimy danemu odbiorcy dostarczyć jakieś urządzenie. No i w tym przypadku symulacja pozwala nam i rozwój w oparciu o symulację pozwala nam na skrócenie tego czasu, tak zwanego time to market. W tym przypadku ANSYS podchodzi do tego zagadnienia w zasadzie Simulation Driven Product Development, tak? Czyli tworzeniu wirtualnych prototypów w miejsce fizycznych, dzięki czemu tą pętlę zwrotną robimy na ekranie komputera, a mianowicie możemy dokładnie zwalidować nasz model, możemy zobaczyć jego słabe punkty konstrukcyjne już na ekranie komputera, czyli zamiast tworzyć fizyczne prototypy i potem wracać z powrotem, my wykonujemy x prototypów wirtualnych, a potem postępujemy zgodnie już z tą naszą standardowym podejściem, tak, do produktu, no i mamy dużą szansę na to, żeby nasz produkt był najlepszy na rynku. Więc tutaj mamy takie dwa przykłady, anteny, ale też silnika. I oczywiście te dwa produkty, tak, możemy bezpośrednio zastąpić wirtualnym prototypem. No i tutaj dla przykładu antena oraz maszyna elektryczna i widzimy wyniki, tak, na ekranie komputera, które bylibyśmy w stanie pomierzyć w laboratorium lub też w jakimś innym stanowisku laboratoryjnym lub też na żywym produkcie. Także symulacja komputerowa pozwala nam znacząco skrócić czas, który wymagany jest do osiągnięcia poprawnego prototypu, poprawnego modelu, poprawnego produktu. Więc symulacja pozwala nam znaleźć najkrótszą drogę, żeby móc zaoferować produkt na rynek końcowy. Jeżeli chodzi o rodzinę produktów ANSYS-a, to myślę, że warto wspomnieć, że to nie tylko i wyłącznie narzędzia, tak jak podczas dzisiejszego seminarium powiemy, do niezawodności elektroniki, ale w rodzinie produktów ANSYS-owych mamy również narzędzia do symulacji przepływów, do symulacji mechanicznych, do symulacji elektromagnetycznych, narzędzia dla konstruktorów, ale też dużo bardziej zaawansowane narzędzia do liczenia chociażby samych struktur półprzewodnikowych. W tym przypadku myślę, że jeżeli chodzi o elektronikę, to na pewno to, co może Państwa zainteresować, to przede wszystkim te narzędzia z pakietu elektromagnetycznego, elektronicznego, ale też na pewno takie zagadnienia jak mechanika czy też termika. Bardzo często jest tak, że termika jest konsekwencją tego, że coś zostało źle zaprojektowane po stronie tej właśnie elektronicznej, więc jest to jakby skutek. Ta temperatura jest skutkiem czegoś, co można nazwać w cudzysłowie zagadnieniem elektromagnetycznym i żeby tego być świadomym. Także jeżeli chodzi o ANSYS-a, mamy pełną, kompletną platformę, żeby zaspokoić między innymi Wasze potrzeby. Także jeżeli ktoś z Państwa będzie zainteresowany, to zachęcamy do kontaktu. Pewnie przypuszczam, że część z Państwa być może nie słyszała o produktach z ANSYS-a, ale myślę, że jeżeli ten temat jest dla Was interesujący, to zachęcamy do kontaktu. No i tutaj chciałbym dosłownie w paru zdaniach powiedzieć na temat tych narzędzi do symulacji elektromagnetycznych. Więc mamy trochę ich więcej niż 6, ale ja wybrałem te 6, które uważam, że są tutaj najważniejsze. Więc pierwszym z narzędzi, które chciałbym pokrótce omówić, jest ANSYS Maxwell. Maxwell jest narzędziem do symulacji pól elektromagnetycznych niskich częstotliwości, czyli w Maxwellu możemy liczyć zagadnienia z elektromechaniki, takie aplikacje jak silniki, dławiki, magnesy, szynoprzewody, elektrozawory. Kolejnym produktem jest ANSYS HFSS, czyli High Frequency Structural Simulator. Jest to dokładnie to samo narzędzie, tak, ale w tym przypadku liczymy pola elektromagnetyczne wysokich częstotliwości. To, czym to się różni od Maxwella, to faktem, że równania Maxwella, tak, są tutaj rozwiązywane włącznie z propagacją tej fali, czyli do takich aplikacji, za pomocą których możemy wykorzystać ANSYS-a, HFSS-a do policzenia tych aplikacji, to są m.in. jakieś anteny, falowody, konektory, przelotki, sprzężenia, tak, pomiędzy ścieżkami, zagadnienia z zakresu EMA i EMC. Kolejne narzędzie to ANSYS SI Wave. ANSYS SI Wave jest narzędziem stricte dedykowanym pod kątem analiz płytek PCB i możemy liczyć w nim takie zagadnienia jak signal i power integrity. Mamy możliwość liczenia również strat w ścieżkach podczas pracy naszego urządzenia, a następnie te wszystkie straty, tak, zarówno z Maxwella, jak HFSS-a i SI Wave'a, możemy przenieść do kolejnego narzędzia, którym w tym przypadku jest ANSYS IcePack. ANSYS IcePack jest zaawansowanym programem, który umożliwia nam wykonywanie analiz termicznych urządzeń. I to, co jest ważne z punktu widzenia tego narzędzia, że on wykorzystuje solver CFD, flagowca, którym jest tutaj akurat Fluent. I to, co jest ważne, że w tych zagadnieniach termicznych uwzględniane są 3 rodzaje transferu ciepła, które właściwie te wszystkie 3 musimy uwzględnić podczas symulacji tych termicznych. Jest to przewodzenie, jest to radiacja i konwekcja. Także te wszystkie straty, które obliczamy w tych pozostałych narzędziach, możemy potem przenieść do IcePacka i poznać konkretną temperaturę, do jakiej nagrzeje się nasza płytka PCB, czy nasz szynoprzewód, a może nawet i maszyna elektryczna. Kolejne narzędzie bardzo unikatowe to jest ANSYS Q3D, ANSYS Q3D. Jak sama nazwa wskazuje, Q jak Quick 3D, jest to narzędzie do ekstrakcji parametrów pasożytniczych dowolnych struktur w 3D, tak, parametrów RLCG, czyli na przykład możemy policzyć sobie albo jakąś indukcyjność, nie wiem, cewki, możemy policzyć chociażby indukcyjności szynoprzewodów w tym przypadku, możemy liczyć ekrany dotykowe, a także możemy policzyć fragmenty, tak, naszego falownika, gdzie te indukcyjności potem będą wpływały również na stany załącz i wyłącz. No i ostatnim narzędziem, który właściwie, z którym możemy łączyć te wszystkie pozostałe moduły, to jest ANSYS Simploleur. Jest to zaawansowany symulator obwodowy, w którym możemy zamodelować całą energoelektronikę i nie tylko. Mamy możliwość uwzględnienia chociażby długości przewodów, tak, którymi zasilana jest maszyna, a te przewody możemy na przykład policzyć w Q3D. Mamy możliwość policzenia modelu, tak, silnika, czy to w formie modelu zredukowanego, czy też pełnego i połączenia go w układzie obwodowym z kompletnym układem sterowania. Także tutaj chciałbym powiedzieć, że właściwie te wszystkie produkty, one też są w rodzinie ANSYS-a. Być może ktoś z Państwa z nich korzystał, ale może warto też zastanowić się, czy akurat tego nie potrzebujemy. I to, co jest najważniejsze, że właściwie te wszystkie produkty, które przed chwilą wymieniłem, są teraz w jednej licencji, czyli posiadając jedną licencję, macie dostęp do wszystkiego, jesteście w stanie zrobić symulacje komputerowe z zakresu pełnego produktu, tak? Od energoelektroniki po płytkę PCB, po silnik, po fragment falownika, po jakiś tam fragment przekształtnika, dławika i tak dalej, i tak dalej. A na końcu jeszcze to może się wszystko w ramach powszechnego obecnie IoT komunikować z innymi urządzeniami do monitorowania na przykład albo też diagnostyki. Także to tyle w ramach krótkiego podsumowania narzędzi, które posiadamy i o których też może warto wiedzieć. Co jeszcze? Chciałbym serdecznie wszystkich Państwa zaprosić również na naszą stronę internetową www.mesco.com.pl. Za niedługo będziemy mieli nową wersję tej strony, która będzie jeszcze lepsza i to, co można na niej odnaleźć, to przede wszystkim nasze czasopismo, które wydajemy 2 razy w roku Messengera, gdzie nasi klienci między innymi chwalą się tymi rzeczami, które im się udało zrobić z naszą pomocą i też samemu. Dodatkowo też możecie odnaleźć ciekawego bloga, ciekawe informacje. Jesteśmy również tutaj twórcą Akademii MESCO, w ramach której za darmo udostępniamy się wiedzą z zakresu symulacji komputerowej, ale też zapraszam na nasze media społecznościowe, Facebook, YouTube i nie tylko. Także zachęcamy serdecznie do odwiedzenia i ewentualnie kontaktu. Nie gryziemy, więc zapraszamy. Jeżeli ktoś ma jakiś problem, to my go z pewnością spróbujemy Wam rozwiązać. Okay, so now I think that we can switch into the English language, and I would like to introduce our guest from ANSYS. So, Andrew Farborder. Andrew has a background in electronic system design, having spent a number of years working in the defense industry before moving into the electronics design and simulation industry, working for companies such as Cadence, Synopsys, and Dassault. And currently, Andrew works in ANSYS as product sales specialist in EMEA for Sherlock, ANSYS PCB reliability analysis tools. Andrew is based in UK. And our second guest, Dan. Dan is a mechanical engineer with PhD from Callas Institute at the University of Maryland in the United States, one of the leading research institutes in the physics-of-failure approach to electronics reliability. He has worked on projects with Delft University in the Netherlands and IMEC in Belgium. as well as many devices and chip makers company. Dan moved to Europe in 2010 and currently lives in Munich. So now the voice is yours, Andrew, so you can share your screen and continue with our seminar.
Thank you, Thomas, and good morning or good afternoon all. So let me just share my screen. Hopefully that's visible to everybody. Right. Do you see that, Thomas?
Yes, we can see your screen.
Perfect.
So the voice is yours.
Okay, thank you. So this is roughly what we're going to cover in this section. So I'm going to give you an introduction to electronics reliability and an overview of ANSYS Sherlock. And then my colleague Dan is going to do a demonstration of Sherlock, show you how it's used, how easy it is to use, looking at and how it integrates within your electronics design flow. Then we come back to a few slides just to show how we integrate to the rest of the electronics reliability ecosystem within ANSYS, before we continue with a little bit more demonstration and then a wrap-up session of some question and answers. So if you have any questions as we go through, and I'm sure Thomas has probably said this already, please put them in the chat and we'll try and address them at the sort of intersection of each part of the presentation. Okay, so without further ado, let me give you an overview to Sherlock. So as I noticed from Thomas's slide, even though I unfortunately can't speak Polish, Thomas talked about the traditional design flow, where you design a product, you build prototypes, you test it, they break, you fix it, and you go through. So that companies tend to involve their products using what's worked in the past, changing only what's needed, using this typical flow. And some studies have shown that actually a significant proportion of development cost of new products are associated with the validation of the design in terms of this test, fix, fail, repeat cycle. And as a consequence, when it comes to producing reliability estimations for the product, these tend to be proven through this cycle or through an amalgamation of MTBF figures for components used in the design. And what's really needed is the ability to reduce the number of test cycles that you do and predict the failures early in the design phase using simulation and gain back some of the time that's spent within this cycle, perhaps to innovate and develop new ideas. And this is where ANSYS Sherlock comes in. So Sherlock uses physics equations and materials knowledge to provide a reliability analysis of the design before you get to prototype. So just to be clear, Sherlock is looking at the mechanical shock and vibration and thermal risk to the board, the components and the solder joints on the board itself. It's mechanically induced failures, the reliability of physics. And Sherlock builds on the information that's produced by the ECAD tools, so the Altiums or the Allegros and the PCB design tools. And through simulation, considering the environment in which the design is going to operate, it calculates a time to failure or reliability prediction for the printed circuit board assembly. And this allows you as designers to make decisions early in the process that can reduce the test cycles, reduce time to market, and impact any potential warranty costs. Sherlock analysis provides these time to failure predictions for component, package, board, and module level as a series of tables and a set of curves, which are Weibull or life cycle curves, as you can see here. And these curves can be for the different loadings that are simulated, whether it's a thermal load or mechanical vibration or a mechanical shock. And you can see it for the individual components or for the whole board. So you can determine the problem areas up front. What Sherlock isn't is a set of actuarial lookup tables based on MTBF figures. MTBF figures have been used for many years, and they're often empirical calculations from tests which are quite historic, based on uniform random failures and averaged over time, giving a constant failure rate. And this just isn't accurate, nor does it really reflect how a device operates in a changing real-world nonlinear environment. So if you look at the curves on the graph representing the different loadings, or indeed the whole board, you can see that we don't actually achieve the required reliability of the board, which is represented by this black box at the bottom, which is less than 10% of failures across 10 years of life. In fact, when we actually run through the analysis, we can see that the board is barely going to make 4.5 years. So again, Sherlock uses physics equations and materials knowledge to provide a realistic estimation, a prediction, a figure for the lifetime of the printed circuit board. And this has been confirmed many times by ourselves and our customers. So the question is when to use Sherlock best to make the most benefit. Well, Sherlock provides most value when it's implemented in the early design stages. So you can start early when you're looking at the initial part selection for some identified key functional blocks. There'll always be a handful of important parts, and you can use these, and Sherlock can run a quick test on these and work out any physical component mismatches. Essentially, at this stage, it's running a quick coefficient of thermal expansion check between the components and between the components and the potential printed circuit board, and provide a yes/no recommendation for suitability. And based on this, you can filter whichever way you want, whether it's cost, availability of the product or the component, manufacturability of the component, and so forth. At this early stage, it's all about avoiding any costly errors later in the process. Once these critical components have been identified, the next question might be, where on the board are they likely to survive? So very often you'll be restricted in terms of the printed circuit board size. And if you put in roughly this size into Sherlock, you can place these components on this board. And you can then use Sherlock to run an early vibrational modal analysis, i.e. that is where on the board we'll see the most movement. And using the assumed physical construct of the board, any likely mounting conditions and so forth, Sherlock can highlight any keep out zones, or green zones, areas of concern. And this can be then passed back to those laying out and routing the board. And in between this initial analysis and the final sort of creation of the bill of materials, Sherlock can be used by each group as they finalize the design. So any changes to components, to the board structure, to mounting points can all be assessed for the impact on the reliability by doing what-if analysis through the design process. And as you'll see in the demonstration that Dan will do shortly, it's a very quick process to do this. It can also be used to help with the design for manufacture process, where it can pass on the maximum stresses allowed for the assembly and test process. And you can understand whether the stresses that the DFM equipment is going to place on the board itself. And finally, another area where Sherlock can be used is to mitigate change management. So if a component that you've got on a board that's in the field needs to be changed due to obsolescence, you can use the components replacement suggested by the manufacturer, put it into your Sherlock analysis, run Sherlock model, run an analysis with the new component, and potentially avoid running any expensive tests in order to prove that that component would indeed pass and maintain the quality and the reliability of the product that you've got. So let's look at the process in a little bit more detail. So a key component of Sherlock is the pre-processing capability, coupled with a huge component and material library. So often companies that are doing and looking at reliability analysis for their products are already using simulations such as mechanical finite element analysis tools. And this actually can be quite a painful process, especially for PCBs, because while FEA is powerful, it's very broad, needs lots of inputs, often expertise. And for a printed circuit board, you've got all of those components, all of the different material of the components, the material of the board, and just the physical construct of it and how it's all put together. So it can lead to quite a complex process to create a PCB model in a mechanical analysis tool with all that material data and so on. And this is with Sherlock, you simply read in the ECAD file that's generated by the PCB layout tool. And within a few seconds to just a few minutes, Sherlock will virtually manufacture that printed circuit board into a 3D model. And the benefit here is our libraries. We have hundreds of thousands of components with all the material properties and sizes and dimensions associated. And we're adding new ones all the time. And Sherlock will equip the printed circuit board virtual prototype, if you like, with this data, from the stack up to whatever BGAs or QFN packages you might have. The library is modifiable, so you can add to it at any time. And sorry, skip the slide. You can add to it at any time by yourself, or in fact, there is a team of librarians based in ANSYS who will take a bill of materials and create a series of models and components and send these back to you, so you have them available for your analysis itself. Once you've got the board imported and a 3D model with all the components and material data assigned, the next step is to characterize your life cycle and the loads that the board is going to experience. So these can be thermal, mechanical, or shock loads in the form of curves, or you can use industry standards, or loads that you use in your test suite, or even customer-specific loads as inputs for these analysis loading. And here, Sherlock will provide a GUI for helping you to define the curves, or as I say, they can be imported from text files or Excel files. And the reliability expectation is entered as a goal as well. This could be the requirement that you have of 5% failure rate over a number of cycles of operation, which characterizes the minimum operational lifetime that you want to achieve your PCB. So with that all set up, with the virtual prototype, with the loading and the requirements, it's just then a time to actually look at and do the analysis themselves. So there are several inbuilt analysis types within Sherlock in order to assess the reliability aspects of the board. The most common is solder fatigue due to thermal changes over the expected lifetime. So here, you know, for each cycle, the board is subjected to, there will be the expansion and the contraction of solder material, which will over time and due to creep, you know, cause fatigue within the solder and eventual breakdown. And what Sherlock is doing is calculating the time until that actually happens. But as you can see from the column on the left, there's a number of different types of analyses built into Sherlock, from CAF failure, harmonic vibration analysis, in-circuit test analysis, mechanical shock, and so forth. And all of these can be run within Sherlock. Okay. So for a typical example of this might be running a shock and vibration test. So you have your generated 3D model, you have your sample shock profile, you apply that within the simulation. You can look at a displacement plot and see how much the board will bend under that shock. And you can start to look at a table which shows the individual components and which components are actually failing because of that. You can look at the life cycle prediction of the components of the board and understand where the problem is. And then you could start to do things like, you know, run what-if analysis to analyze this. And for this part of it, and to show you some of this, I'm actually going to now pass across to Dan, who's going to run, who's going to show you how we sort of import the ECAD, look at the bill of materials and associate with the libraries, look at the component data, show the loading curves, run some simulations, look at the results, and do some analysis and so on. Okay, so Dan, over to you.
Great. Okay, so Andrew, if you want to, there were 2 questions in the Q&A.
Yeah, absolutely. Let me address those questions.
Okay.
Okay. So the 73% number for the assessment of costs on this test, fail, fix, repeat cycle, that's something that's ANSYS didn't do that assessment to estimate it. That is a market-led figure that's been done by companies that specialize in analyzing and looking at workflows. And it's, you know, it's an estimate that's based on a number of tests and from different companies that have you know, provided the information to these analysis companies. And I think that's publicly available figure. If you really want, I can try and look at and find information about that. Corrosion failures and reliability. There is some investigation looking at the corrosion aspects of design and how that affects failure. And more will come on that later. But at the moment, we don't have that built into, unless I've missed it. I don't think we've got that built into Sherlock. Dan will be able to comment further on that as he goes through the demonstration, and we look at the different analysis types that are currently available in Sherlock.
Right. Okay. Then let's get started. So we're just going to do a live straight demo right from the beginning.
Dan, just interrupting. You've got the Zoom window in front of everything on your. We're seeing your screen rather than Windows.
Do I?
Yeah.
Huh. I thought
So
I was
we
sharing.
can't actually see all the Sherlock goodness. So you might need
that's...
to share a different window.
Yeah, you should probably share the different screen. Yeah.
Yeah, I thought I said screen number 1. Okay, I guess not. Sorry about that.
That's better.
Yeah, now we see your screen. Sherlock is on.
Okay, great. Anyway, so let's get started. Right, we'll start right from the beginning. As Andrew said, you can import right from ODB files from ECAD. And that's what we're going to do here. It's also even possible to start earlier where you can create everything by hand, which is, a little bit more time consuming. For the sake of brevity, we're going to start right from the beginning. And you can see right when I just created a project, and all I have right now is a section for my life cycle definitions. You get a sort of a starter pack of loading that you can apply to your project. And they all have just sort of, some default standard values in them. And we'll get to those later after we input everything. So just to get started, we're going to start with, let's see, add a circuit card. Let's call it CCA. It's probably not going to be tin lead. And we will now import our ODB files. You can also, there are a couple of different ways to do this. Let's see, where's our tutorial? You can also just go right here from the project start, and of course I have to scan the archive first. Okay, I'll show you that in a second. Here you see when you start to import everything for the ODB files, Sherlock scans the library and looks for things to match up as it translates things. And here it's looking for now. In the parts list that I found, what's the part description? Well, it's the one luckily called part description, and the part numbers are called part number. This is the easier way to do it. Sometimes you'll have some trouble, but in general, it's pretty easy to match up your information. So it scans the archive and it says, these are all the things I'm going to bring in. Great, so let's bring them in. As I said before, right from the project thing, you can go to import ODB archive, even just to start your project. But I wanted to start it here just to show you that you can already start with a lifecycle section. So we've brought in our ODB files. You can see in the layer viewer, basically everything is in, the components are here. They're all in the right spots. And even the copper artwork, let's see, turn off the components for a second. Even the copper artwork and each of the layers is included. As I said, all the components are in their spots. And this is, so these files here, they're not the ODB files, they are translated files that Sherlock has put into useful form for it. The next bit of information we have, of course, is the stack up. Now, this is the information that came in from the ODB files that has to do with the PCB. And, it's a 11-layer board. It has the one of the great advantages is, it has the copper percentage per area that is based on the artwork that it found in the layer files. And so that will change, of course, what the material properties are for each of these copper layers, because they're not 100% copper. If you remember, let's see, this one's 94.7, that was copper 2. You can see that one's almost completely covered. And that changes what the effective material properties are that, this is almost pure copper, oops, this one. So these are close to actual just copper. But then when copper is only 15%, it has different properties because then it's more copper resin. This is important because here at the top, you see you have a general effective properties calculated for your PCB. This is useful in a lot of different ways. You can see this later when we do a what if analysis and we change some things to try to increase the reliability of our board. Here you can see what changes you do change, like say the in-plane and out-of-plane coefficient of thermal expansion of the board that will help your solder joint reliability and things like that. And also later when we export to different things like on Workbench, sometimes you export a board that is just an effective brick because it's easier for calculations depending on how much precision you have in the project and how much time you have. You can get the properties just as this, or you get your layers out, and then they have each of the layers calculated. Yeah, there's a lot of freedom there. That's about all I wanted to say for the layer viewer. We can go now to the parts list, which is, oops, I had my filter on. These are all of our parts. And in this, you can see that there is a color hierarchy at the top. And this is important because as you go to the left, it's more increasing in priority. Of course, the bottom is just a guess, which is not bad. Sometimes people say guess and they're like, I don't want any guesses on my board. It's not, it's just that, like say here it says that C1 is a capacitor. That is a guess because nothing inside the ODB file specifically said this is a capacitor. However, the reference designator is C1. There's a part number, and there's a form factor, and there's all this other information, material properties that say it's probably a capacitor. I mean, a lot of the information from the parts list that Sherlock gets from the ODB files is sort of interpolated or translated, because we're going from ECAD stuff to more mechanical structural simulation area, and there's a little bit of a translation. And let's see, we can do, first I'll show you how you can update your parts with the library. So we brought these in, well, let's look at the colors for a second. So we brought these in, right? And these are all blue because they're from the pick and place section of the ODB file. Some of them are pink because Sherlock already figured out with its package database what these are for packages. And as I said, since we're doing a more structural analysis with the electronics reliability, because most of these are structural, except say semiconductor wear out, most of these are structural analyses. What is important in this analysis is going to be the parts package type and materials, right? So that's the geometry. This is a 1210, surface mount capacitor. And what's it made out of? It is made out of, let's double click on it and open, double click there. And the package is made out of aluminum, right? And so that, based on the material properties that we saw in the stack up for the PCB, and then the different things that have to do with the solder, these things go into the fatigue models that are used, like say in the solder fatigue analysis. So important here is the package type. There are other variations, that you can get into the manufacturers, the manufacturer and part numbers, and we can talk about that later. But so for right now, you can see that some of these packages were figured out. A lot of these packages were figured out. I mean, most of the things that come in on your board, when you look at the board, right, let's look at the components. Most of these, a lot of your RLCs, your resistors, your capacitors, most of the stuff on your board usually is going to be standard stuff, right? A lot of the hard work is going to come in later with your ICs and your BGAs when you really have any application-specific things, any new or interesting components that you are worried about. It's also generally where the focus is when you're running your analysis anyway. It's not on the simple RLCs. But that being said, right, so we want everything to come in and everything to be filed correctly. Now with the library synchronizer, we have two, you're going to have two libraries. You have your own local part library that you can save either, like on your computer or, maybe a company server. And you have the Sherlock part library. And as Andrew said, the Sherlock part library is maintained by our librarians. And you can have, it's got a lot of stuff in there and it's always growing, especially when people send in bills of material, like he said, to have them created as specific Sherlock library entries to use where everything's filed correctly with all the parts that we were looking at before. As I said, let's look at his, all of these, all of the dimensions and the mount type and what kind of ends it has and what the material is made out of. Like you can have all this done by librarians if you can't find it in the Sherlock part library. But it's not always just that it's not found in the part library. You can, let me see. It would be good if we looked at libraries, part libraries. So let's open up the Sherlock part library. You can look for, oh, this is left over from before. So you can look, if you look in for an exact match of one of the parts that was in here, I think it was this exact match, and we list the parts. And there are no parts found for this, but this part is in our list. And in fact, this part came out as green because also in the background, this the part wizard patterns. Now, there's another type of it, part of Sherlock, that goes and it looks at parts and says, okay, I don't know this exact part. I know part of this part. If we look at, which I'll show you, you look for the prefix, oops, look for the prefix match. And you see, okay, so this is a capacitor from AVX. We didn't get the exact ending, but this part comes in a pattern. They name their parts with patterns. And Sherlock has part wizards where it goes through and says, I know a lot about how AVX names its parts. Maybe we don't have this one precisely, but we know the pattern, so it's probably this. And so when it's when we're relatively certain that we have, when we're certain we know what that part's going to be like because of the pattern of AVX's naming, then we can mark it green and we can be sure that it is correct. All of this has to do with basically just making it faster and easier to get all of your parts in here with, a high degree of certainty that everything's been filed correctly and everything's been done correctly. And let's see. So, oh, and by the way, if you don't know, if something doesn't show up, you can even just go to, you can put stuff in by hand, right? You can, I do this so many times. I have a Mouser auto search in my Chrome, right? So you just come here to, like, say Mouser and then grab the data sheet and open up the data sheet and say, like I said, here's the pattern for AVX naming, which is why Sherlock already knew what it was. And then you can go in here. Well, usually, I mean, this is a simple RC, so the schematic is not that crazy. But then you get the dimensions from this, and then you can go in to Sherlock and fill in your own parts if you have to fill in your own parts. So, but generally, with a project, that's only going to be a couple. Most of them are going to come in either from the part library, especially after you've done a couple of projects. Even your local library is going to cover most of it, right? So that is to say, at this point, we haven't actually done much work. I'm just showing you how it works. But here, we've come in, we've taken in our ODB file, we've taken in our parts list, we've synced our parts list with the part library, and we're almost already ready to do our analysis. The only thing is up here, of course, this life cycle that I was talking about before at the beginning. And this is where you set up the events that you're going to use, the loads for your analysis. And this one comes with, let's see, we'll look at the thermal event here because I want to do a solder joint fatigue analysis. This is the standard one that comes in. You can edit it. You can change, the minimum temperature, maximum temperature, dwell time in each, either by hand or, and I think you can edit by drag and drop. Well, and also load. You can load in, you can save your own list of library of life cycles that you have that you use for most of your projects, and you can save them in your profiles and then pull them up for each of your projects if you want. It's actually even, and a lot of Sherlock stuff is done with CSVs and text-based files. So let's see if we can, where is this? This is in data. Right. So if we look at this, the CSV, you can see it opens. Yeah. So, this is just a standard CSV of a table of values. And you can make your own here. You can have Excel spreadsheets where you have based on maybe your loading profiles, or, if you're like an automotive and you have different requirements for different regions or different loading profiles and different use cases. Maybe you have, storage. You have to do a thermal event of storage in a garage. And then you have a different thermal event for, your average daily use. Then, you can save all of these as spreadsheets and modify things and use them a lot easier that way. So, right. So we have this. You can even, let's see, you can set from your phases, right? This is phase 1, and this one lasts 10 years, and it does one 10-year time. We can make another phase, add a life phase, say this is, like I said, if you have storage. And this is also, let me do this one time, for not milliseconds, that would be ridiculous. 1 year. So this is a storage profile. Right? And so we got to add what? We want to add, well, let's duplicate this thermal event. And then say that's storage. Well, that's fine. We can do it there too. This is just that you can control the properties of how much, if you want to use them separately. Say we're going to do 1 storage and 1 operation per day. If you did 1 storage per day and like 10 operations per day, you can have them in different phases. And at the very top here for your life cycles, you can say, and this is that box that Andrew was talking about on the results curve that we're going to look at. You want to make sure, you say here your metric is that we have to have under, say 20% probability of failure within 10 years. That also has to do with, that doesn't change, anything in the analysis, but it changes how the results are displayed, that box that's on the results and the color coding. Speaking of which, so let's get to that, right? Now that we've done, we've imported everything, we've synced our parts library, we've checked all of our parts to make sure they're in and at the right space, and checked our life cycles and maybe added one that we want to use. So solder fatigue. We're going to run it and then pick both of them to run it as, save and run. And in just a couple of seconds, there we go. Now we have some results. We already have results that we can check. And solder fatigue, which is great. Solder fatigue is one that is one of the biggest problem areas for electronics reliability. One of the reasons this one runs so fast, by the way, is because this one is not a finite element analysis. This one is based on actual analytical and empirical fatigue models that you see, used that you'll see in journal papers when you look up electronics reliability. So now we have our results. Let's see, we have this in, oh, this doesn't have cycles to failure because I ran more than 1 cycle. We can change that. First, let's look at the curve. Now we can see, all right, so this was our reliability metric that we set. We don't want it to go above this line before 10 years, and it did. So we've got some work to do. What we have is not going to work. You can look at, also you can, by the way, so you have the red ones, which I said is, these are the ones that tell you that these are your bad parts. The yellow ones are questionable. They're on the borderline. And the green ones, of course, are good. You can also grab a bunch and then say, well, let's look at just their life prediction. Well, that one was great. That one is underneath the 20% line before 10 years is up. But then, of course, the red ones, not so good. And let's see, if we just do, let me run this. It'd be easier. We can also look at, we could run storage. And then we can look at cycles to failure because there's only 1 cycle that we're running. I think that this, see here now it has how many cycles to failure for each of them and how much that translated into years. That's just because of the math that we put at the life cycle of basically how many cycles we are doing per year. And then of course, by the way, when we did one less thing, the only problem parts now is our U9 and U10 VGAs. So let's see, let us save this. So you can save results, give it a name. And then this is when you can get into your what if analysis. that Andrew was talking about earlier, which is great because now you have, well, let's see, let's close this. This is our current results window, and we'll open this in our results viewer to have next to us while we do some changes. And this is great. It's a great little results viewer. I think you can also you can export these and look at them externally outside of Sherlock, where people can look at the different curves that you have. Well, we only did one, so we only have one curve. I think Andrew showed you in a previous PowerPoint that you will have one curve for each of the analysis sections you run, and then the combined curve that shows you your overall, which is a statistical combination of the other ones. So, and we have, let's see, we did solder fatigue, and here's our table. By the way, issues, sometimes you have I didn't check the package types for some of these. It's marked as radial which is, yeah. These are some of the things that you can edit while you're going through your parts list to make sure everything goes properly. But these small capacitors, I wasn't looking at checking those anyway because I knew from my experience with my own products that this wasn't my problem area. So, right. So we have these saved analyses, and we could do things like we go back to our stack up and say, okay, what if we had, let's see, grab all of our laminates and edit our laminates and say, what if instead of just our regular generic FR4, we went with an FR4 with a higher glass transition temperature? Maybe that helps our situation. Just save right there. Everything's been changed. Then go back to our solder fatigue, run analysis, save and run. It's done. So now we have our now you can see we've already improved some of our danger zone resistors are out of the danger zone. They're in the green now. We still have a problem with our BGAs, but we've already seen an improvement of our design in just a couple of seconds. So then you can do, and there are other things you can do with your, like in your parts list, you go to your, let's see, those were BGAs. Who was in trouble? 9 and 10. And you can look at, so these guys, they're both the same 676 BGAs. And you can look at, say, like I said before, a lot of this also has to do with the precision that you have at the time when you do the analysis. Now, these are standard dimensions for a BGA of this size and number. You could be like, well, you did your failure analysis once you had some components and said, actually, you know what, the ball diameter on the pad side, which would be, this is on the package and this is on the pad. Well, maybe the package diameter was, in fact, 0.5 and not 0.4, right? And then you save that and you say, and it's for both of those. So I was editing U9, but U9 is the same as everything with this part number, so change all of them. And then we've done that. And then we go right back to solder fatigue and run it again. And it's done. Okay, U9 and 10 got better. And U1 and 2 are a little bit worse. Oh, because those are also the same. No, those are LCCCs. Could be that, yeah, when you mess with neighbors, then other neighbors, when you mess with a component, then other neighbors will also get damage transferred to them if you make something more robust, right? So you can see now how you can do very quick what if analysis, changing things. And let's see, but okay. And the last one, the best one, I think, is that, so we've done this. We set up our storage situation that we were using that goes from 0 to 100 degrees. And does everything go from 0 to 100 degrees? Probably not. This is like, say, what the garage temperature would be for some reason, 0 to 100. That's the thing. But just for the sake of argument, That's what the garage. That's what the thermal chamber is when we're running it, right? But that's not what the components. Now I picked storage, so there's no components heating themselves up during this, but it could be that components are heating themselves up. Or of course, things hold heat and they store heat. So you cool the chamber down to 0 degrees. Do the components go all the way down to 0? Depending on how long you sit there, maybe not. And this is where you can do things like, now let's add a file. We have a thermal map, which, if I do it correctly, this is mainly for, let's see, view file. So, we have ourselves an infrared picture of our board during a test. This works best with infrared pictures. Theoretically, you could also do this with, a thermal contour that you got in Workbench. And we'll look at that a little bit later when Andrew talks more about the integration in ANSYS workflows with other ANSYS products. And now let's see. So we take this, right. So this is what it looks like. And how do we use this? Edit the properties of this file. This is, as I said, this is our repository of useful files for our project. And you can always go in here and, you can actually also do it with these too. You can edit all the properties of everything and how it's used in here. And you can also, of course, use it for nothing, say it's unknown. But this one is, I put it there on purpose because I know what it is. It is a thermal map, an image thermal map. And let's set this up. We look at our legend here. The minimum temperature is 30 degrees. The maximum temperature is 47 degrees. And now we have to pick which now what point in time is this picture from? Let's say this was the minimum in storage temperature because, when we cooled down some stuff in the middle, this doesn't make logical sense for the sake of argument. Some of the stuff held heat longer and didn't actually get down to 0 degrees. So we'll apply that there. And now we have our thermal image that we need to edit, right? The map. Align the board. This is, I don't know if you guys have used any of those apps where you can take a picture of a document instead of using a scanner these days. Same idea. You just take it and you move the corners to the around the thing so that it knows it's in oh yeah, got to legend, right? So now we have the board lined up where it is, and then align legend. And this tells it, so what it's going to do is just some pretty straightforward color mapping where it looks at the legend. We told it it's here. It knows the full spectrum of colors, does some interpolation from 30 to 47, and then matches everything. Done, save with this. Close that. You can, let's see, view layer. In our layer viewer, now we can see that everything's been mapped basically where it's supposed to be, and the board is square again. Some of these were supposed to be rotated that we didn't do. That's when you're double checking your board and everything like that, you would do that. And you can see even our temperatures have been interpolated from the legend. And this is pretty cool because now when you run your analysis, right? So we just put that in right now, go to solder fatigue, run analysis on the storage. And you remember from before, our saved results, all of our max DT was 100 because everything was theoretically going from 0 to 100 degrees. And now we have different max DTs for each component because we now specified their own different minimum temperature each time. You can do this for maxima, for minima, for all of your different thermal profiles. You can do this. If this works now, this case, it works best, I think, with the picture for from experimental results. Like I said, theoretically, you could do this with a contour from ANSYS Mechanical. But, well, this might be a good time to send it over to Andrew so he can start to show you some of the integration between, because you can, let's see, before I do that, sorry, I got you, try to get you ready too fast, Andrew, but before I do that, I wanted to say you can add a file. Again, see, that's what these guys are, the thermal maps CSV. Again, a lot of things that you do in here are based on CSVs and text files. So we can open a file here, but if you've used a thermal analysis or any analysis in Workbench, you know that you can take your components. If you did a thermal analysis of your board, you can just pop out an export sheet of the results of, an average or a maximum, depending on how conservative you want to do your analysis of your component temperatures. And then you can make them a chart here and then also put those in as a thermal map, and you can better control what the actual minimum maximum temperatures are, say, on your components. I think that's, so that's a good time. Andrew, if you want to take it away and give more background on the integration into other Workbench products.
Yeah. Okay, thanks, Dan.
One question, so one comment, if anyone have any questions regarding this part, please just put it into the question and answer window, and then Dan can answer these questions.
Yeah.
Yeah.
It's a bit of a whirlwind thing. There are also, once you do start using Sherlock, you can see there are, we have a bunch of tutorials on how to run things. This one, ad hoc project creation, is what I mentioned at the beginning of the ways that you can start stuff just by hand if you don't have any of your ODB stuff yet. Maybe you're doing a what if analysis for what if I use this BGA instead of that BGA. I don't even have my board yet. I know what my board stack up is going to be. You can put that in by hand, make a little square, put a BGA on top of it, two next to each other that you want to test, and then see which one lasts better in your thermal analysis.
So we have some questions, Dan. So the first one is, a thermal analysis is not an analysis, just a presentation. No, you actually do a full a thermal analysis of the board itself. So what you're doing is using, you're looking at the different, as you apply the loads to the board, the components will heat up and they will expand within those loads and then contract. And what happens with this expansion and contraction that's done is that the material degrades over the expansion. It suffers fatigue, okay? And that fatigue builds up over time until it fails. So when and what Sherlock does is it uses calculations and so on, and the material data and models that have been proven time and time again to show how long that if you subject the material, whether it's solder or the components, the leads and so on, to this expansion and contraction from thermal changes, how long that will actually last before the fatigue builds up to a point of failure, where the solder starts to crack and things like that. Yeah. Did you want to add to that comment?
Yeah, that's basically it, right? So it is definitely an analysis. It's not an FEA analysis in that in this particular one for solder joint fatigue, there's no finite elements being built up. This is a sort of classic fatigue analysis where fatigue models are applied, both analytical and empirical. We have, along with our Sherlock librarians, we also have lab services, and they have a lot of back data with a lot of different boards, a lot of different components, and a lot of empirical constants, to use in fatigue models. And that's what that is. When I hit save and run, like that was not like one of these cooking show tricks. That was I did it right there, and it ran all the components through each of the fatigue models that were specific to each of those components based on their properties, you know, and their package types and everything like that. Let's see. And then the, right. And, oh, and by the way, for the thermal map, that one, I had that, this was the thermal map image is just a picture of that tutorial board that I was using during a test, say. I had it in a folder.
I think one comment to add, yeah, that you can take the thermal map from camera, but you can also use the thermal map which you get from the simulation software, right, as well.
You can, yeah. I would actually advise against that because there are more precise ways. You know, like, because when the thermal map, the picture is great and it's very cool tech, but it's just the top, right? And if you want to actually get a better estimate of what this component's temperature is, you know, and you have a simulation, a thermal simulation that you've done, then it's better to export like an average temperature of that package from your, you know, from your ANSYS analysis, because now you have internal temperatures to calculate with. But yeah, you can still do it from, you know, just take a snapshot of your contours of the top of your board from your thermal analysis and also input that.
So we have a question about how to add high integrated components like the CPUs into the thermal simulation itself. So there's two aspects to this question. The first one, at the PCB board level, that integrated component, which could be it could be on a ball grid array type of component for the CPU, or it could be a pinned one, or depending on whichever CPU you look at. Thermal, as Sherlock would look at the individual ball joints and of the component, and look at the, you know, the expansion of and the heat across the board, and see how those solder balls will expand or contract. If you want to look at the component itself, then we have a workflow which allows you to look at the package and inside the package, if you know that package information, where you can actually start to analyze, you know, what might be happening inside the package as well. If you wanted to look at in particular detail over thermal analysis at the different balls, where you know, if it's a particularly large CPU, then you might want to take that into something like a mechanical, and you can export from mechanical. We'll talk about this in a minute. Export from Sherlock into mechanical for a very detailed analysis of all the balls on that BGA itself. I think that would answer that. Any further comment, Dan, on that particular question?
No, like you said, I think that was a good one. That's a good segue into what we're about to do. So maybe we can shelve that for a couple of seconds.
Go on, sorry.
Let's see, what else do we have? The DFMEA tool. Let's see, where did I put? The DFMEA tool is mostly, I believe, just a lookup table where it does, it looks up statistical things in known values for each of these components. That is, you know, like I was saying before, that was this is one of the ones where, like semiconductor wear out, where it is important which manufacturer you have instead of just the package type. But most of this is just, I believe, a statistical lookup. It's like a design check, I guess. And then let's see. Let's assume I have a component available in through-hole and surface mount versions. Will Sherlock help me estimate the lifetime and choose which components to use? Does it take into account how components are assembled, even if they are glued? It can, yes. Depending on how you're building it, right? You can have, like I said before, like if you just want to look at these two components, you can put them next to each other on the board. Well, you can do two different boards. You can have, you know, there's one analysis. And like I said, you do it one way, you save the results, and then you do the other one, and you can change, you go into your, let's see, let's grab a through hole. And then you could say for the leads, is this, well, I should put it on edit if I want to edit it. Right? And you can say, was it a through hole? Well, no, now it's just a leadless capacitor on top, and then you can just run the analysis again now that we've changed the lead types. And then you can just compare the results and see which is better. As far as gluing stuff, there are other things you can add. And let's see, there are ways to add potting and underfill. And that would probably be, let's see, with glue, that might be better with also what we're about to do in the transfer to Workbench, where you can add more details and, play around with your geometry a little bit more and do a more focused analysis on certain components.
Okay. There is also one additional question on chat. Can we include the Sherlock Physics-of-Failure analysis, a heat sink that is directly assembled to an electronic component, to see how it will impact on its lifetime and reliability?
Yes, you can in fact add heat sinks. We have a whole section of, again, for each of these parts in your layer viewer, you can add more things. Add it right here, edit heat sinks. What are we going to do? We want to add a heat sink. And then, fill in the details, if it's fin type, how many fins there are, where it goes. And then you can move it, on top of your VGA, put it there. And then there you go. Then you've got your heat sinks. And can you show electrical in part parameters? I think maybe that was, I'm not sure exactly what that is.
What do you mean by the electrical in part parameters? The electrical, okay, I got it.
Maybe it's this, okay. Right, well, this is, maybe this is a little counterintuitive at the time, because it says that you can have a max rated power that is not, and then you have an applied power. Max rated power is 0.1 because that's what's in the data sheet. Max applied power, if you put something here, it doesn't have an effect on the analysis, because at the moment, Sherlock does not have the ability to run, electrical loads from the components themselves, but it is good for bookkeeping, and it's listed. And then if you do, like we're about to show, when you transfer stuff into mechanical, this also doesn't apply there, but you have the information. This is mostly for, like I said, this is mostly for bookkeeping, so that you can use stuff. No, he wants to spit. That's a little straightforward.
One other comment I would add to this is that the integration between Sherlock and the ANSYS Electronics desktop, which has the other electronics reliability tools in it, such as SI Wave and IcePack and so forth, where some of these values are used, it means there'll be a consistent sort of component model across all tools. So this is potentially for future use.
Right. And then, does the software pick up appropriate probabilistic model depending on failure cause type? Shock vibration. Yes. Well, probabilistic, I don't know if I would say probabilistic, because this is a physics of failure based analysis. So this is all based on fatigue models and failure models that come from, like in the vibration analysis, where actual FEA models are built, and then you run the analysis, and then you get the strain values at like the leads, and then the appropriate failure model for lead failures during vibration is applied in the math, in the background. Can you choose the probability model by yourselves? That's a good question. I don't think there are other tools like the PTH fatigue where you can, no, just quality factors. And right. Properties. Just generated. Yes. So, right. There's no picking and choosing between the different types of failure models you want to use, which is, you know, because this is, as Andrew was saying, this is more of an early analysis and these are all standard and industry accepted fatigue models and tried and tested by our labs. But which is to say, you know, that you can still do it yourself when you transfer these over to Workbench, and you can run your own analysis and get your strain levels, and then, you know, apply your own, you know, Steinberg constants or whatever that you want to use for your vibration analysis, and then you're good.
Okay. So let me share my screen. There's a couple of additional things that I wanted to just point out. So hopefully everybody can see my screen again. So this is
as we can see.
This is thank you, Thomas. This is a simple case study that example, if you like, in slide format. So, you know, you might have your design here, you know, this could be a radio circuit or something like that. And normally when you put together a printed circuit board, things like connectors and jacks and so on get placed first because they need to be accessible for use. And then the next step would be the placing of the complex integrated circuits. Okay, these are the most important part because this is these days, you know, one chip does everything type approach. And so the question is, you know, where would you put this on the board itself, and where do I put it to survive something like mechanical shock? So this is a typical use case for something like Sherlock. So you'd put it on the board, and then you'd run your analysis based on the loadings you've got. And as you've seen from Dan's demonstration, you would get your Weibull curve. In this particular case, we're looking at the mechanical shock or the Weibull curve due to shock of the board. And you see we're not actually achieving our lifetime requirement. And if we actually look at the displacement map, we can see that, you know, perhaps we've placed the component right bang smack in the middle of the board here, which might seem like a good idea because then we can place ancillary components around it. But actually, from a mounting point, maybe we've just got mountings in the corners. This is the worst part to play it. One of the things you can do within Sherlock now is that what if analysis. So you can decide, you know, what are you going to do? Should you move the component to one side and then you can quickly rerun the analysis? Does that have an effect? Or should you strengthen it? Maybe you put in some underfill or something like that, or maybe you put in additional mounting points. Okay. The point is, with Sherlock, you can do all of these things within Sherlock itself. Okay, understand exactly what the fix to the reliability issue is, and then feed that back into the design process before you've taken that step to even create the board itself. So you're mitigating the design risks as they happen. So I just wanted to highlight that actually, you know, as Dan was showing with the thermal side, even with mechanical shock and vibration, where we are actually doing FEA analysis themselves, and we're creating a mesh over the board and the components on the board and the leads and so forth, you can still, it works very quickly, and you can still do the the what if analysis within Sherlock and then feed the information back. So just looking at how Sherlock sort of integrates within the rest of the ANSYS PCB reliability portfolio. If you like, Sherlock can be seen as a pre-processing, as we've talked about, way of getting in and doing further analysis. So you've got the inbuilt analyses to Sherlock itself, but if you want to really start to analyze in more detail, then you have the ability to reach out and export into IcePack, which is the ANSYS thermal analysis tool, looking at CFD flow, thermal flow across your board. If you wanted to put fans on and you know have heat sinks taking away some of the heat, what you can do is you can have a dynamic heating model, which you run from something like SI wave, where you take the dynamic thermal properties of the board, when it's powered up, powered down, and runs under operation. You can take that into IcePack to look at how the temperatures and so on change, and then feed that information back into Sherlock to understand how that would affect the reliability of the board itself. Similarly, we can export with one click out from ANSYS Sherlock into mechanical, where again you can run structural integrity analysis, and you can start to look at things like elastic mounts or cases and assemblies, you know, maybe there's you know, one of your cables is a particularly long cable that might be pulling on a connector and fastened to a connector, and you want to see the stresses and strains that long cable is going to be placing onto the connector and onto the printed circuit board. Then you would go out to mechanical to really analyze that. And we have these links to ANSYS Mechanical, to LS Dyna, and so on to allow this detailed analysis. Similarly, you know, we can link out into tools such as Minerva for the data and process management, and keeping it all together. We can link out into OptiSlang, so you can run sort of an optimization type cycles to improve things or find the best position for things and so forth, and start to automate some of the activities that you are looking at doing. So some of these are still developing. Sherlock was acquired by ANSYS in 2019. The solvers that Sherlock uses internally now are the same solvers that ANSYS uses in its tools, so that, you know, it's all based on the same MAPDL type solver, and these integrations are developing as we go forward. Okay, just a couple of notes about these integrations. So Sherlock exports to classic IcePack. I mentioned briefly that we are also connecting through to the ANSYS Electronics Workbench, or desktop rather, and thereby we'll be able to export EBD models out of data out of Sherlock and into there. So there's better integration with the likes of SI Wave, where, you know, you could potentially use the same component data that comes in from Sherlock in SI Wave calculations and so on. And the idea is, by exporting into IcePack, is you're driving this more accurate thermal simulation when you're really looking at details and thermal flow and so forth across the board itself, as that becomes more important. Similarly with ANSYS Mechanical, there's a good workbench integration, which simplifies and expands on the mechanical capabilities of the tool. So there is actually built in a pre-processing block and a post-processing block, which allows you to read in the Sherlock project, set up any analysis in there, but also allows you then to put in your different types of analysis and bring in different features and so forth. So maybe you've got housing constructs and things that you want to bring into a broader mechanical analysis, and then you can feed the results out of that into a post block and get the reliability figures out of Sherlock for this larger system. And you know, across a design team, you'll have the electronics engineers, PCB engineers, thermal engineers, and so on, all wanting to use their particular tools and look in detail at their particular part of the analysis. And Sherlock enables this by allowing this sort of integration between the two and this sharing of the 3D printed circuit board virtual prototype model, if you like, to do that. Okay, we're very quickly going to go back to Dan. He's going to show this easy export into Workbench and so on, and then return to the presentation for a quick wrap up.
Great. So, right, we can start with, now, as I said, well, you can grab any of the analyses which have to do which make an FEA analysis if you want to export the model to Workbench itself. And then let's see, which you can generate it here. We're not going to, which takes some time, and I guess we want to get to the Q&A section soon. So we will just export here. Let's do, now actually first I want to do workbench file. Let's just call it export. So you can see there are a couple of different options that you can pull from. You can even get a straight APDL script for any of you who are into that, which I am. A CDB model, the workbench journal file, step file just for the geometry, and also IcePack. Here we go. And here you can pick how complex you want your model to be. In the interest of time, you're not going to have some things like the leads and everything, but we'll have the PCB and the components. And then we just export. It takes a while because, so what it's doing in the background is it is exporting that step file that I mentioned before and making a Python script basically that ties it all together. Sometimes people get a little frustrated at how slow ANSYS works sometimes. And that's because, well, a lot of this has to do with the interoperability that I mentioned before about working with text-based things, which helps because, you know, then it's also modifiable when you need to. I always say that one of the biggest strengths of Sherlock is that it's highly customizable. And one of the biggest challenges for Sherlock is that it's highly customizable. So these are, you know, it's a power. You got to know how to use it. And sometimes you got to pay in time while you sit, like now, as we wait for everything to get translated. You can see it has built in the workbench layout, all of the engineering data. That was all the material stuff that we had before. And as before I mentioned, you know, on the layup for the stack up window, you can see the effective materials box at the top. And so those are the materials that are going to be in our board here, because when we exported, we selected just an effective brick for the board. You could also actually even export it to have all the layers of your PCB to be separate, you know, and have your laminate and your copper, because sometimes you need to know what's going on in the board. There's also even a different workflow where you can do different types of trace mapping depending on, you know, because you can imagine if you have all the traces on your board and the length differentials between the traces in your giant BGAs, you know, the mesh on there is going to be almost untenable, depending on how much time and computing power you have at the moment. You know, that can be a huge pain. So here we have our board exported. We haven't meshed it yet because it came in nice and easy. And here we have all of our materials that have been shipped with it from Sherlock. And let's see, all of our components are here. We don't have any leads because it's faster when you do it that way. In this case, you know, you could do things, you could lock it down at the corners, you could run a vibrational analysis, which of course you can also do in Sherlock. But in this case, you know, now that we have it in Workbench, we can do more tweaking if we need to, depending on our design. You know, we can, like you go to your connections, like one of the questions mentioned, and we can, you know, change the contact regions, change, you know, maybe it's contact and no sliding, maybe it's glued. We can do things like this to change and see how the analysis changes when we do that. And so that was the old and still, you know, the main way of exporting the model from Sherlock to Workbench. And one of the new things I think with 2021 R1 is, or it might have been 2020 R2, I don't remember, but they added in these blocks, the pre and post block. And so now you can have, let's see, actually, if we wanted to put in, there's like a modal. And let's see, in 2021 so far, the only way is to import a project. I think in the next release, you can start fresh from Sherlock here, but we would have to, let's see. Yes. But here, you know, since we already have a project that we made, we can import it this way. And then you would take a bit of time, send the setup here, and then make sure you share this project from the beginning to the end. The reason there's pre and post is because you basically, you take everything from the project that you had, you take all of those analyses that were here, basically, you can do all of these and more, or in more detail than here. You know, you can also, you can play with your mesh better when you do it in this case. You know, maybe your leads, you say, I don't like the meshing on that J lead. I would like it to be tighter. Then you come in here and you do it yourself and you make a tighter mesh. And then you have the, send the solution from your analyses. You can have a bunch of them out to the life prediction here, because what the life predictions do is, like I said, it takes the strain data from the FEA, if it is, or in the case of solder joint fatigue, from the calculated fatigue models, and takes that strain data and then puts that into fatigue failure models based on the strain data. What would be the cycles to failure estimate, which are again based on the different component types, solder types that are used, and a lot of empirical constants determined from literature and from the vast experience that we have in the Calc labs, in the Sherlock Lab services. Let's see. I think that was right. Well, that's the workbench one, and I have. You know, I mentioned before, this is not a baking show, but I do have this one already imported from, because well, the ice pack one actually takes a lot longer. This one has to read in a whole script, and it takes, I don't know if any of you used ice pack. This is one of the slower analysis tools in the family. But so you can import it into here and say, if you have like some fluid cooling going on underneath, you can import this, your board here. You can have, you can see all of our stuff. And then you can, in this case, actually, one of the reasons I wanted to use this one, this pre-baked version, is because you could also say import. Oh, that's the bottom. That's why we can't see it well. Now you can see that you can bring in a case like this in ice pack and do better with, you know, maybe you got, maybe you have an opening at the end and you have air blowing through to cool it and stuff like that. So you can get better results for your thermal situation this way. You know, and then you can get your thermal contours at the top. And as we were talking before, you can take those data and then import them back into Sherlock as for more specific thermal states, depending when you do your solder joint fatigue analysis or what have you. I think that's, and let's see, I don't have the electronic workbench version, but yeah, that is also coming if I'm correct, Andrew. Do we have, what's the state in the, I don't remember the state in the next release, 2021 R2. I know that there is more functionality in that one, and I think it also is wrapping it into the ice pack inside electronic desktop better.
That's correct. So 2021 R2 will have our first integration of Sherlock within the electronics desktop from ANSYS. So yeah,
right on. Okay.
Okay. Let me share my screen. So thanks, Dan. So.
Okay, one comment to add. Yeah, that the ice pack in IDT environment is much more user-friendly, and the interface is working way faster than the classic one. And yeah, so yes, that's for me also good information that it will be possible to connect the Sherlock with new IDT ice pack. That's really great information. Thank you.
No, absolutely, and we recognise that that I figured DFR Solutions, who developed Sherlock, had the integration with IcePack Classic from a few years ago, but we've been working hard to create this this integration into the electronics desktop because we see, you know, the use of SI Wave integrated with IcePack, integrated with Sherlock as a real game changer for how reliability can be considered across the tools.
Yeah, and if I could add, because I was, I used to work in power electronics, and especially with, with all the electronic motors coming, and all of the power control modules for those, and the power modules there. The fact that, like, in my workflow, I used to have I would do an ice pack model, and I would, calculate the thermal resistances, and then I would hand it off to the thermal guy, and he would build a thermal network on, what everything would be, to be able to determine what the power generation for the chips are, because that there's a feedback loop with chips. The amount of heat that they're generating, it also depends on how hot they are, and how hot they are, of course, depends on how much heat they're generating. And so we have to do this iterative loop between like 3 different departments, where I would do the thermal resistance analysis, and the thermal guy would build the network, and he'd give it back to the component engineers, and they would recalculate the amount of heat being generated during the board, and then they'd give it back to me, and then I'd recalculate everything. And then, which is, like you said, I'm really excited about this to get into AADT too, because then you can, one person doesn't have to change desks. You can do that all yourself. And that's going to be, hopefully that's going to be a lot better.
Thanks, Dan. So just to summarize what we've shown this morning, or this afternoon rather, is Sherlock provides a very fast pre-processing facility, bringing in the ECAD data and the libraries, and creating this 3D printed circuit board model for analysis. And that's in minutes instead of hours or even days. If you've tried to do it, you'll understand the benefit that brings, and that'll have a significant impact on any sort of design flow. It also democratizes the FEA use. It's a simple GUI. And under the hood, the FEA analysis enables any users, whether it's electronics engineers, thermal engineers, mechanical, PCB, reliability, and so on, to go and investigate that printed circuit board and understand, the impact of vibration, shock, and thermal environmental conditions on that printed circuit board, all before, remember, the first prototype is even created. So it's helping avoid redesign, saving on test costs due to having to retest because of failures. And this allows the quality and reliability to be communicated through the electronic supply chain, providing these reliability figures up and down the design into the next department, and also to end customers. And in fact, there's even a locked IP model available to enable sharing of the reliability data to perhaps a broader and bigger system analysis. And of course, it enables the understanding of the reliability of the product in the real world environment, reducing the chance of any warranty issues from happening. Okay, just a couple of sort of references and so forth, examples. So Continental Automotive, they're big users of Sherlock. All the sort of circuit boards and so on that they develop to go in cars and vehicles are run through Sherlock and tested in terms of reliability. Similarly for Valeo, and there are papers that are available that you can access through the internet, which goes into how and they're using them, and how they're using using Sherlock. We have Danfoss drives use Sherlock and have benefited significantly from reduction of the time to test their designs and build them, and also finding problems, which means that they reduce their time to market for any new products that they're creating. Western Digital have done similar things. They've managed to eliminate a number of design reviews and a number of test vehicles for their disk drives and so forth, and getting to market nice and early, saving costs as they go through. I've mentioned Continental already. Other automotive car makers utilize Sherlock in looking at the power electronics in particular, and how those are used. And there we go. So just to wrap up now, are there further questions and answers or question sessions that we can address?
Okay, just one thing to add, that at the end of the session, so if you end the meeting, there will be some kind of the quick survey. So we'll be very grateful if you can fill up the survey, and that will help us. You can also put there additional comments if you would like that we can contact with you. And maybe before we start this Q&A session, one additional things to add. If you would like to test the Sherlock, please contact with us, and we'll be happy to share with you the trial license. And yeah, so if you have any additional questions, please just contact with me, with Masco, yeah, and we can help you. Yeah, so now let's continue with the Q&A, because I'm not sure if all the attendees now will be to the end. Yeah, so if there are any questions, please just put it into the Q&A window, and we can try to answer for all of your questions. Well, one question maybe from my side, as I'm understanding it good. Yeah, when there are no, let's say that I have some PCB, and where there is no, let's say, one specific part, that means that I can write an email to ANSYS, and there are some librarians, yes?
Yeah, so one of the benefits of Sherlock is the very large library. We have hundreds of thousands of manufacturer components available. So when you load your design into Sherlock, you'll have a bill of materials. It may come in through the PCB information, you know, the ODB++ file or something like that, or you may load it in separately. Inevitably, even though we've got hundreds of thousands of components, there will be some components that are probably missing. What you can do is you can send across that bill of materials to us here at ANSYS. We have a team of librarians whose job it is to create models of these components. And this is why our libraries are always growing. And they'll basically take your components that are missing their data. They'll find the data sheets for them. And as long as these are sort of off-the-shelf components, not custom specific components, and they can get the data from the manufacturer, then they will create the model and package it up in a library and send it back to you. In which case, you know, you can then utilize it within your Sherlock analysis. And this is a free service, so we provide this for free. So we have a question. Space electronics often use hand assembly. This means we are applying the tin in a different way, and we elevate the components to limit stress tests. Are there such models for the available components? How to approach such a case? So you have the facility within Sherlock to look at the model itself and specify how the model is attached to the board, whether it's a plated through-hole type attachment or whether it's a surface mount type attachment. And you can specify the different lengths and so forth of the leads. And obviously, what Sherlock will do is it will take into account those lead lengths and the heights off the boards and so forth in terms of the mechanical expansion, contraction, or vibration properties. And it will use that information in the calculations. Similarly, if you glue or pot your components down, you can apply that potting or that glue and the material information of that into the analysis and understand how that will affect the Sherlock analysis. You have the ability to create and change the components yourselves, make customized components. So all the component models are there and available to you. Dan, do you quickly want to, if I stop my share, do you want to quickly show that that sort of screen and the component package modeler?
Yeah, you can, as you said, you can, there's a bunch of different lead geometries that you can pick from, including, and then you go to, let's see, you can go into your lead height. It tells you what that dimension is and how you put it in. Well, we did a gull wing here. Yeah. So you can change your geometries if it has to do with leads. You can also be, if you pot the entire PCB in resin, you can actually also do that. There is, let's see, we have from the, let's see, edit, where's my plotting regions, right? So add a plotting region. Check that out. You know, the whole thing is plotted. Well, I get. Yeah, and then you can, you know, so you say, well, you can do one on the top and one on the bottom, and how thick it is, potting standoff, all these things, basically. You can add your potting to the board. And then, yeah, if you do anything that's like, I don't know how, you know, like you said, there are special conditions for like a lot of the space electronic things, soldering by hand. You know, if you have, like we were shown before, you know, this can change sometimes your solder joints. This has an assumption based on the fact that a solder joint thickness is going to be probably, where am I going? Part properties. So this is printed like, say, maybe by wave soldering, and there's a stencil thickness like that. And so the solder joints generally will be half that size. And so that's the default that it gets for all the solder joint thicknesses for this board. You can change that. Or if you're doing stuff by hand, which means a much less uniform but more controlled system, you know, then you can go to each of your components and say, well, you know, like we were saying before, you can change the solder dimensions, what the thickness is for each one, and even the pad sizes too, because these also come in standards from the parts library or from the data sheets that I showed before. The standard suggestion by the manufacturer of how big the pad size should be for each of these components. But maybe for increased reliability, you have bigger ones. So you can come in here and you can change these. Again, you know, you can change all of your lead geometry and your pad sizes and everything that increases depending on the special needs for your components. And if there's anything, you know, if you have a lead geometry, say, that nobody else has, you can, a lot of times you can actually sort of pick something close and then tweak the geometry to make it look like that anyway. And, you know, bottom line is, if you're not happy with that, then you can do the thing where we just export it to Workbench and then more closely define, you know, the geometry of your leads, and then you can run it that way. Then you get your strain levels, you pop it back into Sherlock with the post block, and then you can have all of your fatigue models applied to your stuff.
There is one additional, probably last question.
Right.
Yeah.
Yeah. The import PCB from Altium Designer. That is a good question. I should know this because I know of. It depends on how you can export with Altium, and I'm pretty sure you can do. There are a bunch of different. Basically, there are a bunch of different types. We used ODB in this tutorial because it's one of the easiest and best way, you know, best importers into Sherlock. You can get CADIF files, IPC 2581s, GenCAD, Eagle files and stuff like that.
Yeah, you should be able to export an ODB++ file from Altium Designer. We have a number of customers that use Altium Designer in Sherlock.
Okay, it looks like we answer for all the questions. So maybe to make a very, very short summary, I would like to thank you, gentlemen, for making such a nice presentation for us regarding the electronics reliability. I'd like to thank you a lot. And if anyone of attendees have any questions, please just contact with us, and we try to answer all your questions, and we'll be also very happy to give you a trial license of Sherlock if you are interested in, or if you have any other questions regarding the simulation, we are also happy to answer all the questions. So thank you very much for attending. Thank you, Andrew. Thank you, Dan. And I wish you a good day and good weekend.
No, thank you very much for your time. I hope it's been of interest. And as Thomas says, if you have any additional questions, then please send them through to Thomas, and we'll be more than happy to send through answers and provide more information. And as Thomas says, you know, Sherlock is available as a free trial license. So yeah, if you wanted to try it out, then you know, please get in touch again with Thomas.
Yep. Thanks for having us. This was great.